Hey everybody, Mr. Stone here again. Let's keep going on optics, wave optics. We just talked about double slit diffraction. Let's talk about some different phenomena involving diffraction as well. Hopefully you remember last year where sound could diffract through an aperture of some sort. So any waves can, if they strike an aperture, are able to diffract. So what does that mean for light? Now, you may have seen this, you may have thought about this in terms of some of the things you saw last lesson. There's some weird phenomenon happening here. So, this was the image that I showed you of double slit diffraction. So all those little tiny fringes represent constructive and destructive interference from the two different slits. But the question is, what's the overall envelope? Why does it seem to be very bright in the middle, then sort of drop off about here, it sort of drops off, and then it gets bright again? Why does the pattern get weaker and then brighter on the sides? What's the purpose of that? Well, there must be some sort of reason. The individuals, this bright spots and the dark spots in between, that's from the double slit diffraction. But what about the outside? What about this sort of envelope? And really the reason is because of the slit itself. If I cover up one of them, I'm going to end up with this pattern. This is the diffraction pattern that actually happens just from there being an aperture. Okay, this is purely from there just being a tiny little opening for this, in this case, this red laser to go through. It's able to actually interfere with itself just through one opening, which makes sense because of the diffraction patterns that we had seen from waves through a single aperture. Okay, so we have double slit diffraction, but we also have this single slit diffraction. Now, why does this happen? And the reason it happens because the source itself is not a point source. Okay, we cannot produce light from a zero-dimensional point. Okay, it has to have some sort of width, whether it's one-dimensional or two-dimensional. We have to have some sort of finite width. And what that means is that the gap itself, let's say if here this is our little gap of width W, the gap itself has a bunch of different spots along it. Let's number them 1 through 12, where the light, using Huygens principle, is basically being emitted by these. You can imagine these as 12 individual point sources. So the width, we have to imagine it as an infinite number of point sources, but to help our minds understand it, let's label them 1 through 12. We have 12 individual point sources, and they're all going to send out light towards a screen. And just using geometry, they look parallel here, but they're not quite parallel. There's going to be slight path differences. Again, this is the whole point of all this. This is why there's interference. It's because of this spatial path differences as we go from the source, the slits here, to our screen, where we're actually observing it. So if we consider the point 1, and then a point, let's say, down here at 6, that's halfway along. So there's going to be, if I make a little triangle here, there's going to be a little path length difference. And if that path length difference is a half of lambda, there's going to be destructive interference. And if I go from the top to the bottom, if that path length is equal to an integer of lambda, we'll have constructive interference. Okay? So there's going to be a certain point from 1 to 6, let's say, or I think 1 to 7 actually makes more sense, 1 to 7, where we're going to have destructive interference for that path length. But then the same will happen for 2 and 8, 3 and 9, and so on and so forth. So we're going to have this path length difference again at this angle theta. Okay. Now what that leads to is a little bit trickier than with double slit diffraction. This leads to, because it's the half the width, this leads to a very similar intensity pattern, but notice that we have a central maximum that's twice as wide as the side fringes. In double slit diffraction, we had a central maximum that was all the maximum were all the same width. In double slit diffraction, we have twice the width in the central maximum. And now this is where confusion can happen. Okay, the mathematically it looks very similar, but there are just some subtle differences. Now for a dark spot, we have to have integer number of lambdas. Okay, so if we go back here just to make this clear, okay, so when the path length difference theta between the top and the bottom of the slits is n lambda, okay, so from the top to the bottom, that's n lambda, the path difference between the points from the top to the middle is going to be half of that. So when the path length difference, so the full path length difference is equal to some integer number of lambda, okay, that leads to interference between the top and the middle, right? So then we have destructive interference for n lambda. In the double slit diffraction, we had constructive interference because the path lengths were in phase at n lambda. Now with single slit interference at n lambda, path length difference, we end up with destructive interference because the halfway points are canceling each other out. All the midpoints or any sort of half length, say 3 to 9 or 3 to 10 or 2 to 8, any of those pairings are going to be at a path length difference of half. Okay, so that's a complicated idea. Maybe you should stop the video and think about that for a little bit. But the point of that is this leads to there being a dark spot at n lambda. So that first lambda difference has a dark spot. So it's basically like double slit diffraction, but everything has been shifted outwards by n lambda over 2. Okay, we have that half shift on the inside, which doubles the central maximum, and which kind of flips all the math, right? So previously a bright spot was n lambda over d, but now we have a dark spot at n lambda over w. Okay, and notice that our numbers start at 1 and not 0. Okay, so for single diffraction, you got to be very careful. Either of the diffraction, you have to be careful which formula we're using. Okay, and the only difference here is instead of d, it was w now for the width. And the same thing for the bright spots. It's now what was the dark spot or dark fringe equation from the double slit diffraction. And also notice that we can still use the same sine theta equals tan theta approximation. But again, we're going to have to start everything at 1 and not 0 because of that shift in everything. And again, if it says maybe I don't know, the third order bright spot, so there would be the central maximum, and then this would be the first order bright fringe, and this would be the second order bright fringe. So if it asks us for that, we just have to count, right? So it'd be 1, 2 and a half, right? So that'd be 2 and a half. So m in that case would be 2. Right? So subtle differences between the two equations that you guys have to be careful of. Right? And again, just a quick little comparison between the two. This was double slit diffraction on the left and single slit diffraction on the right. So notice all the fringes are all equally spaced in double slit diffraction, but in single slit diffraction we have this twice as wide central maximum, 2 delta y over here. Okay, compared to here where all the delta y's are the same. Okay, and just be careful mathematically, the equations are flipped. Yeah, so notice that the central maximum twice as wide. So whenever you see this sort of image of this double slit diffraction, the double slit diffraction is actually just the tiny little fringes everywhere. There's still single slit diffraction as a sort of envelope over the whole thing. So we actually have in this image, you're seeing double slit diffraction of all the little fringes, but then the slit itself, each opening itself, is diffracting on itself. So we have and it really makes sense, because otherwise, using the double slit diffraction just by itself, it should say that the intensity of the light is the same. It never tells us anything about intensity of light overall. So it really, mathematically, we had it in the last lesson, all of the bumps should be the same, but that doesn't make sense, right? You would imagine that if I'm shining a light at an opening, most of the brightness would be in the middle, and that as we go outwards, it would go down. And you'd think there would be some sort of normal distribution as a sort of a bump, but really it has these extra fringes from the slits themselves diffracting. Okay? So that's pretty complicated. You may want to stop and go back, and or even just stop and think about this for a second and look at the equations. Make sure you write them down and go over them again. Okay? Let's do a quick example here. So let's say we have light. We have a laser pointer. It's a red laser pointer. It's 670 nanometers, and I'm firing a 12 micrometer slit. And there's a screen 30 centimeters away. How wide is the central maximum in degrees and centimeters? And what's the separation of all the minima except for the central? So what's the space between would be all these guys here, these delta y's? I know it's showing the bright spots, but it'll be the same as the dark spots for small theta. All right, so first one. So we know that there's going to be a dark fringe, the first one, if n equals 1, when the w sine theta, which is the path difference. Remember in the picture, the width times sine theta is the path difference between the top and the bottom of the slit. That has to be equal to theta, or n theta, but we know that this is the first order one, so that's going to be n equals 1. So w sine theta equals lambda. Right? So the angle is just going to be the inverse sine of lambda over w. And plugging in our numbers, I get 3.2 degrees. Now we got to be careful here. So that's telling us that it's 3.2 degrees between the central maximum and the first dark fringe. So to get the entire central maximum, I'm going to have to double that angle. So it's 6.4 degrees. Right? So the whole central maximum is 6.4 degrees. So again, this is less than 10 degrees, so we have no problem using the sine and tan approximation, which is what we're going to use for part 2, where now instead we can just use this, the sine theta is x over L. Approximately, it is really equal to tan theta, but it's approximately equal to sine theta for small angles. And we're just plugging in our numbers. You get 1.7-ish centimeters. But remember, that's only the distance from the central maximum to the first dark fringe. So again, we have to double it. And using sig figs, we get 3.3 centimeters. Right? So that's how wide the central maximum is. Okay? So remember, that's not saying, so the first number I got, 1.67, that tells me the distance between the, let's see, that's the, if I have my like this, so that's telling me the distance between the top and the first dark fringe, so I have to double it to get the whole thing. Okay? So now we know that the difference between all the dark or bright fringes is just going to be equal to lambda L over D, using, that should be a W, sorry, using the similar arguments from lesson 1, and then I can plug it in and I get 1.7 centimeters. So the space between all of them is really just this number here. Okay, 1 point, but to round it to 2 significant figures. Sorry, that should have been a W. That's the width. I must have copy and pasted that from lesson 1. Apologies. All right, so here's some problems. Same idea. I'll work through those. Pretty straightforward using these equations, but be careful now. Maybe write down somewhere like a cheat sheet as to which formula you should use, and maybe draw a picture so you don't get confused between the double slit and the single slit equations and the order of each one. Keep in mind, double slit diffraction does not have a twice as wide central maximum. Single slit does. So we got to be careful of how the order works for us to find where the dark fringe is. Is it that extra little half step over or not? Okay? So that's single slit diffractions. Now, next thing, diffraction gratings. These are very useful things in terms of any sort of, it's like a prism. It's like a super prism, the diffraction grating. If you, in Mr. Francis's chemistry class, whenever you did the little spectroscopy unit you did, and you looked at flames and the colors, and you used a little spectrometer, that little black triangle, inside there's a tiny little diffraction grating that took the light from the Bunsen burner and spread it out into the colors, and you can actually see them all. Okay, how they work is very similar to a double slit. Double slit produces an interference pattern, right? So why don't we put more? Same spacing apart, but a whole bunch of them. What that does is it causes more destructive interference to happen. Okay, it causes more fringes. There's more opportunities for light to pass through, but most of them are going to get canceled out. So if you see in the picture here, this is only 2 slits. I'm going to end up having just bumps for each, right? The integer path length differences. But then if I have more of them, I'm going to end up with more bumps, but most of them are going to cancel out, and it's going to sharpen the peaks. And here at 16 slits, I have these very, very sharp, distinct peaks of where the light is. So it basically works like a double slit, but it just intensifies the pattern. It basically works like a prism. It splits up the light because it depends on lambda. We haven't actually talked about this, but notice that these angles depend on lambda. So if I send white light at these things, any of these, like a single slit, double slit, or a diffraction grating, I'm going to spread out the light. It basically works like a prism. That's an interesting point about a single slit. A single slit, it actually does depend on lambda. So your cameras, the aperture in your camera actually produces a rainbow pattern on the edges. It actually produces this chromatic dispersion, we call it, which actually can mess up some of your photos at some points. We'll talk about that later. Okay, so diffraction grating is basically just a double slit, but a whole bunch of them that just sharpen up the things. And you can actually see these in CDs. CDs basically store information by burning holes into a very thin piece of metal. They use a bright laser that burns these little holes, and they act like the ones and zeros that store the information. So they're basically it's basically like a very, very long line of these things, but wrapped around. And because all these rings are very closely spaced, they're actually spaced at 1.6 micrometers, I can actually use it as a diffraction grating. That's why CDs or DVDs or Blu-rays or anything, they actually have this rainbow pattern on them from the light that's hitting, the white lights that's hitting them. It's this diffraction grating made up of all these rings and spreads the light out. It disperses the colors. But we can actually use this to calculate things like wavelength of a laser. If I shine a laser at a CD player, I'll get a reflection, a central maximum reflection, just a normal reflection, but I'll also get these other reflections which are caused by the diffraction. And the first bright fringe is 23 degrees away from the central reflection. We can use this to calculate the wavelength of the laser because we know this formula, right? The path length difference, d sine theta, has to be equal to an integer multiple of lambda. In this case, we're going to say m equals 1. And then plugging in our data that, the spacing between them is 1.6 micrometers, and the first bright spot is at 23 degrees, so sine 23. I find that the laser that I'm pointing at this is 630 nanometers, which is an incredibly small measurement. You'd have to have some sort of a very, very high-powered microscope, electron microscope, basically, to measure that number. But using light and using the very, very fine tooth comb of the electromagnetic radiation going up and down, we can use that to calculate the wavelength of light. Very cool. If we were in the classroom, we would do this experiment. We would do this with a DVD and a CD and see the differences between the spacing, and use a Blu-ray as well. Unfortunately, we can't do that, but here you go. Okay. So that leads us to that idea I just talked about. That notice all the equations we've derived so far have a lambda in them. So the larger the wavelength, the more diffraction there is. The farther apart these fringes will be, the farther apart the light gets spread out. Okay, so different wavelengths interfere differently than others. So they actually spread light out. And we call this chromatic color dispersion. So spreading of colors. Fancy way of saying it, chromatic dispersion. And you can see this in thin films like a soap bubble or gasoline. If you see a small gasoline spill, you can have a very, very small amount of gasoline spill or some sort of oil, and it'll make a sort of rainbow sheen. CD players as well, prisms, any sort of diffraction grating will produce this dispersion. That's why anytime we have these things, we'll talk about thin films, we'll talk about bubbles, later, with why that happens. But know that these things depend on lambda. So their colors depend on, the colors that you see depend on lambda. And we call that dispersion. All right. And last thing I want to show you guys is something really cool. So iridescence. So here we have a blue Morpho on the left, butterfly, and an Anna's hummingbird on the right. Now these colors don't actually exist. These are not pigments. These colors actually are made by nanostructures in their feathers or scales on the butterfly wings that actually act as a sort of a diffraction grating that pick a color for us to see. The blue Morpho is not blue. There's no blue pigment at all there. It is just a reflection through a fancy diffraction grating made of nanoscale things on their feathers or wings. I'm going to add a link to some of the physics here. It's very interesting physics. Some things that we only discovered recently mathematically have been evolved by nature a long, long time ago. Okay, so check it on the Weebly. There's a link to some of the physics of butterfly wings and iridescence. This is called iridescence. You can't talk about the math, it's too complicated, but it's just too beautiful to pass up. Okay, so here's some more practice problems on these single slits and double slits. Okay, so this is the same ones I already put on there, so just a repeat. Go through these and have fun. All right, so again, I hope you guys are all staying safe and enjoying the beautiful weather. Remember, what are the 3 rules? Right? Okay. I'll be talking to you later, and best of luck.